Hi everyone, I would like to give you a review about the papers A Hierarchical Latent Vector Model for Learning Long-Term Structure in Music from ICML 2018. Variational Auto-encoder has been applied to various generative applications, but they have very limited application with long sequential data. In this paper, the author introduced a new type of decoder to learn long-term structure of sequence by variational auto-encoder. The proposed method can learn very long structure of music bar. We all know about the auto-encoder. A low-dimensional representation is learned by an encoder. Such representation is called latent vector. A decoder then learns to reconstruct the input from the latent vector. We often use neural network as encoder and decoder. Everything in a normal autoencoder is deterministic. Therefore, an input is hard-coded to a latent vector. As a result, the latent vectors are only available for data points in the training data. This makes the learner latent space discrete. To overcome this problem, we can smooth out the latent space. We don't learn a fixed latent vector for each data point, but a distribution. The parameter of that distribution is given by an encoder. Then a latent vector is sampled from that distribution. An encoder tries to reconstruct the input from that latent vector. Since the input data is not available for generating, the encoder must learn to make all the distribution close to a target distribution. After the VAEs get trained, we sample the latent vector directly from the target distribution without the encoder. As you can see in the figure, the learner distribution is assumed to be Gaussian. The encoder produces means and variance for that Gaussian. We call this structure variational auto-encoder. Loss function of VAE contains two terms. The first term can be interpreted as reconstruction loss, and the second term is the distance between learner distribution and the target distribution. We often assume that the distribution of latent vector is Gaussian and the encoder produces the mean and variance for that distribution. In the training time, as you can see in the left figure, we need a sampling operator, which is not differentiable if we keep it in the original form. And to go around this problem, we need the reparameterization check. Instead of sampling directly from a Gaussian with the mean mu and the variance sigma, we sample a vector epsilon from a Gaussian of zero means and identity variant matrix. Then the epsilon is multiplied with the sigma and added with mu to get the final latent vector. As you can see in the right figure, the model now is trainable from the encoder to the decoder. We don't need and we are unable to train the distribution of the epsilon. The VAE can help us to manipulate the generated data very easily by changing the latent vector. As you can see in the figure, any image between two images can be generated easily by interpolating a vector between them. Then the output image contains attributes from two original images, but in different degree. By averaging all the latent vector of data that have an attribute, for example, brown hair or red hair, we can get the attribute vector of brown hair or red hair. If we subtract the brown hairs from the latent vector, then add the red hair vector, we can change the hair color of the output image. And if we cannot control the attribute this way. The latent information is ignored by the decoder. We call this posterior collapse. In this paper, we care about the VAEs that their encoder and decoder are recurrent neural network to handle sequential data. In the previous work, VAE used simple RNNs for both encoder and decoder. Data goes through the encoder, and the last hidden state is used to compute the mean and variance of the latent distribution. Then the latent vector is used as the initial state of the decoder, which is another RNN. The decoder reconstructs the inputs auto-regressively. Simple recurrent VAEs have a critical drawback. Only one latent vector is used for auto-regressive generating. RNNs often ignore the latent information after few steps because RNN use the learner information from previous steps. As you can see in the figure, influence of the initial states may vanish after very few steps. The idea to go around this problem is generating the initial state for each non-overlap subsequent from the latent vector and force the RNN to use that latent information as every step of the subsequence. As you can see, by using this way, the influence of the initial states will be decreased slowly. And the proposed model contains an encoder to learn one latent vector for the input, and a conductor to generate initial states for each subsequence, and a decoder to reconstruct the output. The encoder is a bidirectional LSTM to compress long-term structure of the input to a single latent vector. In the encoder, we can use bidirectional LSTM, but we cannot do that in the decoder. The encoder gives two hidden state vectors for forward and backward direction. The vectors are concatenated to a single vector. Two fully connected layers are used to compute the means and variance from that vector. We obtain the latent vector z by sampling from a normal distribution with that mean and variance. A hierarchical decoder generates output for non-overlapping subsequent of the outputs. A RNN called conductor uses the latent vector z as its initial state and auto-regressively produce embedding vectors for every subsequence. A bottom layer decoder uses the embedding vector to generate subsequence. If we divide the output into U subsequence, the conductor produces initial embedding vector, one for a subsequence. An embedding vector is then fed to a fully connected layer to get initial state for the bottom layer decoder. But this initial state vector is also concatenated with the output of the previous step to be input of the current step. It will force the decoder use the latent information. In this paper, they also choose to model the music because US-UK music exhibits long-term structure, and they also cannot generate the waveform. They can only generate the musical note, and the softmax activations is used at the end of the encoder. And the proposed method can be used to generate multi-stream output. In that way, it treats the streams as orthogonal input or outputs and uses the separate encoder-decoder for each input and output, but they share the same latent vector and conductor. The dataset that will be used for experiment is the MIDI files crawled from the internet, a very large dataset. Firstly, the author compared the reconstruction quality of the flat decoder and the hierarchical decoder. When we use the gauge to be the input of the current step, there is no big gap between two methods, but when we use the output of the previous step, performance of the flat decoder drops much more than that of hierarchical decoder in case of the very long sequence. As you can see in the table, the authors also proved the ability of latent space manipulation by interpolating an attribute vector arithmetic. For interpolation, the author do the interpolation in the top left figure. You can see the normalized Hamming distance of the proposed method is closest to the data. In the bottom of the left figure, the coherence of the interpolated data is measured. Lower is better. The proposed method gives the best coherence. For attribute vector arithmetic, the author chose 5 attributes in the MIDI files, as you can see in the right figure. The vertical axis is applied attribute and the horizontal axis is measured attribute. The left is adding and the right is subtracting. You can easily see the effect of adding or subtracting the attribute. There are some small side effects. Finally, a listening test is performed. The listener is asked to choose the most realistic sample. And of course, the real data is still the best realistic, but the gap between output of the proposed method and the real data is not too large. And the rate of flat decoder is much lower than that of the rest. The strings readout in the RAM may be caused by the bias of the listener. Let me conclude the paper. These papers offer an effective and simple way to model long-term structure in sequence data by using a hierarchical decoder. This structure of decoder outperforms the flat decoder in terms of quality and reality of generated data and the latent space manipulation. This structure can be easily applied to other generation tasks. Thanks for your listening.